with readmission rates for both acute myocardial infarction, congestive heart failure. This is of great interest nationally.
Excess
rate national data
Hospital readmissions. We're no strangers to the pain of waiting great lengths for medical treatment, and we're not unfamiliar with the hassle of having to return to the hospital after being prematurely released. In fact, we're so familiar with this that according to Statistics Canada, 1 in 11 patients are readmitted to hospitals within just 30 days of being discharged. More surprisingly, this statistic is not only a tumultuous inconvenience for patients, but it also poses an economic threat to hospitals. Over 2.3 billion Canadian dollars are spent annually on covering the expenses surrounding patient readmission, to be exact. That's a lot of money. Reducing the need for patient readmission would contribute to significant economic relief for hospitals in areas including but not limited to patient care, time, staffing, and resources. It would save many headaches for the patient and their family, and not to mention support their safety and recovery. To combat this economic challenge, we propose the development and implementation of a machine learning tool through the lens of an ensemble model that predicts the probability of a patient being readmitted to a hospital within 30 days of discharge, as a preventative measure. We identified 2 main questions we wanted to answer. How can predictive models prevent patient readmission in an optimally cost-effective manner that minimizes false negatives? And does limiting readmittance and prolonging the length of stay during initial admission equate to lower resource consumption? Our model yielded a precision score of 74% and an F1 score of 46%, indicating that patient readmission is both predictable and preventable, and we're going to show you how. Let's start from the beginning. How did we get here? As with any problem that requires analysis, we first perform data collection. Our data comes from the Discharge abstract database provided by the Canadian Institute for Health Information from fiscal years 2015 to 2021, which details administrative, clinical, and demographic information on hospital discharges, including deaths, sign-outs, and transfers. Our data's recency is advantageous because it reflects economic fluctuations that occurred before and during the COVID-19 pandemic. Its variety in variables to choose from and direct connection to Canadian health data also lead us to believe that it is a credible dataset.
Though our big dataset is, well, big, the sheer number of features, which is 158, suggested that if our model was to be built on this dataset, it'll very likely be subjected to the curse of dimensionality and heavily skew performance negatively. Additionally, the dataset lacked the target column that our model is looking to predict. As a result of these factors, we needed to perform extensive data processing. We noticed the dataset assigned every patient a unique code which was used for identification for future hospital admissions. Using the unique patient identifier as well as their discharge and admission date, we created a binary target column to record whether the patient was readmitted within 30 days of their previous discharge. To eliminate noise and improve performance, 8 features were picked for dimensionality reduction after careful analysis. The columns included age group, gender, total length of stay, the ICD diagnosis code identifying the diagnosis or condition considered to be the most responsible for the patient during hospitalization, and the CCI intervention code that identifies the most important and resource-intensive intervention performed on the patient during their stay. As the final step in data processing, we divided the dataset into training and testing sets using an 80-20 split. We decided to create a stacking ensemble model, which uses a meta-learning algorithm on our training dataset. We do this to learn how to best funnel predictions from 2 or more base machine learning algorithms. We chose this model because we wanted to implement multiple predictor models on our training data and compare their predictor scores. In our background research, we noticed that there was a knowledge gap in general patient readmission predictors because they relied on predicting the readmission rates for specific treatments and lacked generality for all hospital admissions. We believe our stacking ensemble model fills this gap and combines well-performing algorithms that can be used to predict readmission rates for multiple treatments, prioritizing efficiency and accuracy. To fill our ensemble funnel, we developed 5 submodels: Light GBM, XGBoost, Random Forest, Logistic Regression, and Naive Bayes. Both Light GBM and XGBoost are scalable, distributed, gradient-boosted discussion tree models. These have seen a rise in popularity in recent years due to their speed and performance benefits. In both methods, a sequential decision tree will be built by another tree.
Random forest classification is also a tree-based method. The key difference between random forest and the previous gradient-boosted models is that random forest uses an averaging approach, where it takes the prediction of its subtrees and ultimately predicts the majority, whilst the gradient-boosted models use a stacking approach, where results of previous trees are calculated and added up for the next tree.
Logistic regression is an extremely popular model due to its simplicity and interpretability. The model can be used on dependent variables that are categorical in nature to predict probability in which an outcome will occur. In our case, the binary column of whether a patient will be readmitted within 30 days.
Lastly, naive Bayes classifier is a classifier that's based on Bayes' theorem, which calculates the conditional probability of the outcome occurring based on previous circumstances. It's extremely popular due to its simplicity in terms of mathematical and statistical background, as well as due to its speedy nature.
Our next step was to minimize the cumulative error of the ensemble model. To do this, we performed hyperparameter tuning on each of the submodels, excluding random forest due to how computationally expensive it was. Typically, hyperparameters are parameters within a model that have a known effect on the model, but it's not always obvious what the best value should be. The idea behind this was that if we improve the performance of each of the submodels through hyperparameter tuning, this would further improve performance of the overall ensemble model. Though the tuning process for each of the models was slightly different, they all revolve around the idea of cross-validation and random grid search. K-fold cross-validation, otherwise known as out-of-sample testing, is the idea of splitting the training set into k-equal samples, where each samples take turn at being the test set, while the other k-1 samples are used as the training set. Cross-validation is a powerful tool due to the fact that it gives more accurate information regarding the algorithm's performance, eliminating the possibility of the model's performance being attributed to random chance. Unique where a search space is defined, where each dimension represents the possible range of values for a hyperparameter, and each point within the space represents a model configuration. An exhaustive grid search would require iterating through every point in the search space and training every single model configuration before deciding on the best performing ones. The obvious downside to this approach is, with an increasing amount of hyperparameters, in addition to the cross-validation for accurate reports of performance, the approach becomes quickly computationally expensive to the point where it is infeasible. Let's suppose you have 5 different hyperparameters where each of the hyperparameters can take 10 different values. This means that you'll be evaluating 10 to the 5 or 100,000 models, where each model you also have to perform cross-validation on. This is obviously a little impractical. An alternate approach we took was using random grid search, where we specified the number of models that we wanted to train, in this case 10. From there, 10 random points in the search space were selected for us to perform cross-validation on. From here, we took the best performing configuration from these 10 different models.
The Discharge abstract database also included an additional geographic dataset, which included the following numerical features: expected length of stay, ELOS, and resource intensity weight value, or RIW, which is a ratio that measures expected use of resources associated with different diagnostic, surgical procedures, and demographic characteristics of an individual. A clustering algorithm was conducted between these two features to determine if there was a negative correlation between expected length of stay and resource intensity weight value. And this was done in an effort to ensure that reducing readmission rates truly results in reduction in cost and resources. For our particular use case, we decided on the k-means algorithm, which is an unsupervised algorithm that groups data points into k groups based on Euclidean distance. And so we chose this algorithm particularly due to its speed, effectiveness, and simplicity. After deciding on the best performing configuration in each of our submodels, we placed them into the ensemble model and trained it on the entirety of the training set. The model, when used to predict against testing sets, yielded a precision score of 74% and an F1 score of 46%. The clusters created from our k-means algorithm shows high density clusters between resource intensity weight values of 0 to 325 for lower extended periods of stay. And so this supports the fact that there is a lower cost associated with the emissions for the first few extended days. And so with more extended lengths of stay, the cluster center value begins to rise, indicating that a longer period of stay leads to a higher resource intensity weight value. However, it is still more cost efficient than going through the process of readmission. And so the implications of this study are to validate the use of hybrid ensemble models for economic cost prediction. Investing in robust, efficient, and predictive models can allow hospitals to focus more on patients rather than incur the utility and bureaucratic costs of readmission. Our model supports the idea that preventative measures are both possible and cost-effective using machine learning models. Waiting to discharge a patient could be a long-term economic benefit, disguised as a short-term solution. And after all, the goal is to never see them again. See you never.